In section 5-6, we're going to look at the second part of it called scientific notation. So in this chapter, you will learn scientific notation. That is, numbers that are expressed in the exponent of 10 raised to the power of n. So many scientific problems deal with very large or very small numbers. Distance from the Earth to the Sun is approximately 93 million miles. The wavelength of yellow color is the light is about 600 nanometers. To express these numbers a little bit more conveniently, we choose the power of tens to explain the numbers. So scientific notation is a shorthand method used to write these numbers in the power of 10. For example, 93 million miles can now be written as 9.3 times 10 million, or it can be written as 9.3 times 10 raised to the 7th power. This is much more convenient to write than the number itself. So in some sense, we can write the number in this format. Also, when we looked at the wavelength and we saw all of the numbers after the decimal point, presenting that number in papers requires a lot of usage of zeros. Sometimes mistakes are made. So in this particular case, we have 600 nanometers, and it can now be expressed as 6 times 0.0000001. But we can make the change to the power of 10. 6.0 times 10 to the negative 7. To write a number in scientific notation, we move the decimal point in the original number to the right or to the left until you obtain a number greater than or equal to 1 and less than 10. For example, if we had a number of, say, 100, we could move the decimal point over 2 and write it as 1 times 10 to the 2nd power. So you count the number of places you have moved the decimal point to obtain the number in step 1. If the decimal point was moved to the left, the count is to be considered positive. In this case, when we did the 100, it was in the positive direction. If the decimal point was moved to the right, the count is to be considered negative. We multiply the number obtained in step 1 by 10 raised to the count found in step 2. The count found in step 2 is the exponent of the base of 10. So now we're going to write each number in scientific notation. So in part A, in 2010, the population of the United States was about 309,500,000. Notice that we are trying to bring the number, this number here, over to the first position where we have 3. So when we do that, we count how many places over to the left we moved. 1, 2, 3, 4, 5, 6, 7, 8. So we notice that 8 is put in the exponent position of the 10. And we now can write it as 3.095 times 10 to the 8th power. So part B says, in 2010, the population of China was about 1,348,000,000 people. So we can write that by moving the decimal point from here over to here and count the number of spaces that we had to move. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that 9 is our exponent in base 10. 1.348 times 10 to the 9th power. Now in part C, we're going to take the wavelength of an X-ray, which is about 0.00000000492, and convert it into scientific notation. It's not very fun to say all the zeros. So again, what we do is we move the point over all the way until we get it to the 4, and we count how many places we moved. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places, but we moved to the right, so it's negative. So we have 10 to the negative 10, but our number is 4.92. To change a number in scientific notation to a decimal notation, we observe the exponent on the power or the base 10. If the exponent is positive, we move the decimal point in the number to the right, the same number of places as the exponent. And sometimes we have to add zeros to the number after the actual number itself so we can get the right form. If the exponent is negative, we move the decimal point in the number to the left, the same number of places as the exponent. Adding zeros may be necessary. So now we're going to convert from scientific notation to a decimal notation. We write each number in a decimal notation. For part A, the average distance from Mars to the Sun is about 1.4 times 10 to the 8th miles. So to change this, we see that we have the 8, and so we're going to do, when we move the 4 over, we have how many zeros left. So we write down 1, 4, and now because we move the decimal over 1, we're now got the power of 7. So now we have 7 zeros. 1, 2, 3, 4, 5, 6, 7. And now we put in our commas where they need to be, and we end up to having 140 million miles. Part B says the half-life of uranium-235 is about 4.5 times 10 to the 9 years. So when we start writing, we write 45. We notice we've moved the 1 decimal plate over, so we subtract 1 from the 9 and we have 8 zeros left. 1, 2, 3, 4, 5, 6, 7, 8. Now we put in our commas where they need to be, and we see we're at 4,500,000,000 years. Again, we're going to convert from scientific notation to decimal notation. The average grain size in siltstone is about 1.35 times 10 to the minus 3 inches. When we convert that, we notice it's a minus 3. So we're going to put in 1, 3, 5. We're moving the decimal 1 over to the right, so we have to subtract off a -3 to make it now -2. So now we just add 2 zeros and we put a point there. So now we have 0.00135 inches. A millimicron is a unit of measure used for very small distances. 1 millimicron is about 3.94 times 10 to the minus 8 inches. Again, what we do is we write point, and now we subtract off, because we're moving the 3 over, we're subtracting off from the 8 one of the zeros. So now we have 7, 1, 2, 3, 4, 5, 6, 7, 3, 9, 4. So that's what we get. We get 0.000000394 inches. So now we're going to multiply numbers in scientific notation. It's relatively easy. We just rearrange the numbers by the commutative property and multiply the numbers together, and then multiply the base 10 numbers together. And so in this particular case, we're going to multiply 2.1 times 10 to the 5th by a number of 9 times 10 to the minus 3. When we do that, we notice that we rearrange the numbers. 2.1 times 9, that's an easy way of knowing how to multiply that. That's just 18.9. And now when we multiply the base 10 numbers, we can use the laws of exponents. We can just add the exponents together, and we get 10 to raised to the second power. So we have a number 10.9 times 10 to the 2. We know that 10 to the 2 is 100. We multiply 100 to 18.9, and all we have to do is move the decimal over 2 places, right? And we get 1,890. So now we divide two numbers with a lot of zeros in them. So we're dividing 0.0000000000048 by 24 billion. We write the answer in scientific notation first, and from the decimal notation we get 4.8 times 10 to the minus 11 divided by 2.4 times 10 to the 10th. So now what we're going to do is, again, we're going to rearrange this by multiplying this fraction by this fraction. So we'll do that in the next slide. So from the last slide, we had this notation. We separate the two fractions, which we can do under the commutative property of multiplication. And we now can divide 4.8 by 2.4. We see that that number is just 2. And now we can use the law of exponents, where 10 raised to the minus 11 divided by 10 to the 10th is nothing more than 10 minus 11 minus 10, which is now 2 times 10 to the minus 21. Well, that concludes our section on scientific notation in Chapter 5.6. Please review your problems and try to do the problems of the day.